And we had graph number 4. Just a reminder, in the calculator, we're radian mode, we're parametric mode. And we had, oops, let me just, nope, don't want to do that. So that number 4, and we're going to go through a little bit of how the calculator works, make certain that we're going through things. That number 4, we had 5 cos t, and then we had 3 sine 2t. Nope, that's a t sine 2t. And we had that curve.
Why does yours graph so fast?
We can tweak the adjustments in the calculator. What I just did is I changed my window, so I've got everything entered and the equations entered in. Under window, reading through things, and we've got our equation that we've got our x and our y up there. The t min is going to be 0. The t max is going to be that 2 pi. So t min is where it starts. It's 0 for this first, and it's going to end at 2 pi. Well, 2 pi is 6.28. The t step, and this is something I want to go through because we tried to do this one by hand, and it was questionable at best. That t step is how often we plot a point. Now I've got negative 10 to 10, negative 10 to 10 for my x and y min max. Mine graphs quickly because probably the t step. When we were doing this yesterday, when we did it by hand, we were trying to go, we plotted t equals 0, what happens? T equals pi over 2, t equals pi. We used intervals of pi over 2. So our t step was pi over 2, and it gave us that line. You can't actually see anything on this graph because it's hidden in there. But if I hit the trace button, what that does is it puts the little turtle on the graph, for us, and then I can hit left or right. Actually, I'm going to hit right because I'm starting at time equals 0. There's our coordinate, x, y. If I hit the right button, it says t equals 1.57. That's going up to pi over 2. Well, that's going to be at that location. If I keep on hitting, the turtle marches along the graph. So it's there. There's the turtle. There's the turtle hidden in there. If I turn off my axes, don't just watch, but if I go and I turn off my axes, go back to the graph. There's the curve that we had when we did this by hand. We were plotting, we had 5, then 0, then negative 5, then 1, and it ended. Well, as soon as we put it in the calculator, we got a little bit more. If we change the t step is how many points are being plotted. If we go 0 to 2 pi at pi over 2 intervals, it's plotting 5 points. The calculator plots a point, plots a second point, draws a line that connects them. If we've only got 5 points, that's really not detailed enough. And if we do, after that, I think we switch to pi over 4. If we put in pi over 4, we get the bow tie looking. But it's not very good. It's point, 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 point. It connects points in a line. So the finer the t step, the more points that it's going to graph, and the more accurate it's going to be in there. So if we make it 0.01, there it goes. And it takes its time. So now it's going a little bit slower because it's plotting 600 points. And it's plot a point, connect a line, plot a point, connect a line, plot a point, so forth. So the t step, there's a balance between large numbers, small numbers, depending upon what we have. I'm going to turn my axes back on. Now here, if we realize, oh, my t step is too small, I need to stop it. I don't want to wait. If you hit the on button, it stops what it's doing, so then you can tweak it or you can change. So if you hit the on button, it will stop what it's doing. I'm going to go in, y equals, my t step, I'm just going to make 0.1, and it graphs faster. It's less detailed, it's less fine, but it gets it done faster. That might be why mine's going faster. You can change the t-step, how often we plot a point. So we've got that graph. Hey, that's kind of fun. That was called a lemniscate. We'll get more into that later. Comments, questions, concerns? Let's graph the other ones, if we haven't done so already. Number 5, we can just plug in what we have. Just a little bit of play around with the calculator. So number 5, y equals, got 2 minus t squared, and we've got t minus 1. Need to change our window, change our t-step, our t-min, t-max. So I've got the x equation, the y equation. There are the t values. When you go into window, t-min is -3, t-max is 3, so -3 to 3. T-step, 0.1 should be fine. There it goes. How's that look? T-min, -3, T-max, 3. When we're going through, we have a starting point, we have an ending point. So if we watched what was happening, it started and then it ended. So we do need to indicate where we start and where we end. If we draw an arrow, it gives us a direction. Direction going around our curve is important. Parametric equations are all about what's our location at a specific time. We're comparing really 3 dimensions in here. We've got x, y, our position, as well as the time that we're at that specific spot. I can see that in the calculator. If I hit the trace button, I get a little turtle on the graph. So as I march, I can follow the time increasing. And I can see that, okay, there's the motion going along. So that's the idea behind parametric equations, is that we have this motion over time. Does that graph make sense based upon the equation? Excuse me. Based upon the parametric equations with which we started? Oh, we've got x squared, or t squared. Think about something squared should be a parabola. Usually we're thinking y equals x squared. Well, we'd have a parabola going up. We've got x though. X is worth t squared. So the x is going to be a parabola. But it's also negative t squared. So it's a parabola opening to the negative side of x. So that's how that can make sense. Yeah? How's that look? We good? We all right? Let's do the last one. I like the last one. Last one's fun. All right, I got cosine 2 pi t. And I've got t squared minus 4. Nope. T squared minus 4. We're going from -2 to 2. Let's actually change that. We're going to make it more interesting. No, don't change it. Let's keep it as is. Not yet, at least. Pay attention to the way that it moves. Zoop. Look at that little bit there. That changed the lighting. Is the lighting okay there? It's good. All right. Let's get like this little thing in there. Let's expand it. So I'm going to go -5 to 5. I'm going to change the t-step to go -5 to 5. Let's see what happens. There it is. Got that. I'm going to turn my axes off so we can see a little bit more. Zoop. Isn't that fun? What's that look like? Does it look like anything? I see a spring. I see a spring. Little thing on the carnival. Oh yeah, where you gotta slide the ring around the rotating thing that is impossible. I see kind of a spring where it's bunching up down at the end. But it comes down and it stops right there. Well, why does this make sense? Why does this graph make sense? Well, cosine. The x is the cosine. So if we compare t, as t is going by to the x, well, cosine, it's up and down and up and down and up and down. It's just happening vertically. So the t, the x is cosine in time. So the x should be going back and forth. They're left and right. The x is going back and forth because it's cosine of t. The y is x squared. Let's change this a little bit. Rather than negative 5 to 5, let's see if we can get more squiggles down to the bottom, because they kind of just stop there. Let's see if we get more squiggles down there. Let's change our t min, t max so it keeps on going. Should we increase the minimum, or rather make that more negative, or make the t max more positive? All right, let's, what do you say, 10? 15. All right, change the t max to 15. And there it goes, and it's exactly the same. So we changed it to 15. It's exactly the same. 20. Doop, 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 doop. 20, exactly the same. What? Oh, maybe we should have actually made that negative 20. And it's a little bit slower. Where is it? There we go. Doop, doop, doop. Oh, it's exactly the same. Huh.
When t is 0, does it like go back the way it got there?
Does it go back when t is 0? We're going to change something on the calculator. I'm going to go back because I don't want to do negative 20 to 20 because that takes too long. Let's make it negative 10 to 10. I'm also going into y equals. Y equals, I'm going to tweak how this is represented. So at the equation, I'm going to arrow to the left. I'm going to highlight this box over on the left. Now, if you have a color calculator, it'll be like blue, in a line. If I hit enter, it changes the line style. Now you can see that if hitting enter once turn it into a thick line for me. If you've got a color calculator, you can change the color, you can change the line style. I want to change the line, so we have this little key looking thing. To me, it looks like a key. What's going to happen is this is going to be a bubble that's going to leave a trail. So we can like see, I don't know, a little car moving along, leaving a trail there. So I hit enter on one of these calculators until you get a little bubble. Otherwise, change the line style. Now when I go to graph, all right, there it comes down. We get the little bubble, there it goes, there it goes, there it goes. Back and forth. Oh. And then it goes right back up the same path. So it wasn't that it couldn't keep going. It was going, but it had to go back up top. Cosine goes back and forth and back and forth and back and forth for the x. Well, the y is t squared. What does x squared look like? That's our parabola. Well, the y went down and then back up. It hit the minimum. It went down and then back up. So that's because we actually had that t squared. If you look at the lowest point that it reaches, is the negative 4. So if we put my axes back on, check the lowest point that it reaches. Boop, 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 boop. It goes down to negative 4. And just like y equals x squared minus 4, then it starts heading back up. Look at that. How's that look? Point is how we can use the calculators. We've got that different style there. I've got a problem for us now.